In 1997, IBM's Deep Blue beat world chess champion Garry Kasparov. It was humanity's biggest AI achievement, and it could do exactly one thing: play chess. It couldn't tell you what a cat looked like. It couldn't write a sentence. It couldn't even play checkers. Fast forward to today. You can pull out your phone, ask an AI to write a movie script about zombie accountants in the style of Shakespeare, generate photorealistic images of anything you can imagine, and have it debug your code while explaining quantum physics in the voice of a pirate. And that's just Tuesday. What the hell happened? The journey from barely able to beat a human at one specific game to can do almost anything you throw at it took less than 3 decades. But the story actually begins much earlier, in the 1950s, when a small group of scientists made an audacious claim: we can build machines that think. They had no idea they were about to trigger a 70-year roller coaster of spectacular breakthroughs, crushing failures, bitter winters of abandoned research, and unexpected renaissances. They didn't know that their field would nearly die twice, only to explode back with a vengeance. And they definitely couldn't predict that by 2022, an AI would become the fastest-growing consumer application in history, reaching 100 million users in 2 months. This is the story of artificial intelligence, a field that went from science fiction fantasy to touching every aspect of your daily life. It's a story of brilliant minds, broken promises, unexpected heroes, and the relentless human drive to create something that might one day surpass us. That's why in this video, now, we're about to trace the entire history of AI, from the very beginning to the explosion happening right now. The year is 1950. World War II has just ended, and the world has witnessed something unprecedented: electronic computers. These room-sized machines, built to calculate artillery trajectories and crack enemy codes, proved that machines could do math faster than humans. But could they do more? Could they actually think? Enter Alan Turing, the British mathematician who had helped win the war by breaking Nazi encryption. In 1950, he published a paper with a deceptively simple question: can machines think? But Turing was smart. He knew that defining thinking was philosophical quicksand. So he proposed something practical instead: a test. If you're chatting with something and can't tell whether it's human or machine, does it really matter? The Turing test was born, and it gave AI researchers their first concrete goal. But Turing wasn't alone in dreaming big. In 1956, something extraordinary happened at Dartmouth College. A young professor named John McCarthy organized a summer workshop, and he needed a catchy name for this new field of making machines intelligent. He coined the term artificial intelligence. That summer workshop became legendary. McCarthy was there, along with Marvin Minsky, Claude Shannon, and Nathaniel Rochester. These weren't just scientists, they were believers. Their proposal was breathtakingly confident. We propose that a 2-month, 10-man study of artificial intelligence be carried out. The study is to proceed on the basis of the conjecture that every aspect of learning or any other feature of intelligence can in principle be so precisely described that a machine can be made to simulate it. Every aspect of intelligence. 2 months. 10 people. Yeah, they were a bit optimistic, but their confidence was intoxicating, and it sparked an explosion of research. Within a few years, AI programs were doing things that seemed genuinely intelligent. In 1952, Arthur Samuel created a checkers program that could actually learn from its games and improve. By 1959, it was beating human champions. Alan Newell and Herbert Simon developed the logic theorist in 1956, which could prove mathematical theorems, and even found a more elegant proof than the one in Principia Mathematica. The early AI researchers were absolutely convinced they were on the verge of cracking human intelligence. Marvin Minsky famously predicted in 1967 that within a generation, the problem of creating artificial intelligence would be substantially solved. Herbert Simon declared in 1965 that machines would be capable of doing any work a human could do within 20 years. The media ate it up. Popular magazines ran breathless stories about thinking machines that would soon be driving cars, translating languages, and maybe even replacing human workers. Universities poured money into AI research. The government opened its wallet. This was the space race, but for the mind. And for a while, It seemed like the hype might actually be justified. AI programs were playing games, solving algebra problems, proving theorems, and even understanding simple English sentences. MIT's Joseph Weizenbaum created ELIZA in 1966, a program that could mimic a psychotherapist's responses. People knew it was just pattern matching, but they still opened up to it emotionally. The field was exploding with optimism, funding, and wild promises. AI researchers genuinely believed they were just a few breakthroughs away from human-level intelligence. They had no idea they were about to hit a wall. A big one. The first cracks started showing in the late 1960s. Those impressive early programs, they worked great in carefully controlled toy problems, but they completely fell apart in the real world. Chess programs could barely beat amateur players. Translation systems produced hilariously bad results. And despite all the confident predictions, nobody was even close to general intelligence. The uncomfortable truth was becoming clear. Intelligence was way harder than anyone thought. Way, way harder. And the methods they were using, symbolic reasoning, logic, and rules, had fundamental limitations that no amount of clever programming could overcome. The golden age of AI was about to end, and it was going to end badly. The crash came from an unexpected place. A philosopher with a background in physics named Hubert Dreyfus. In 1965, he published a paper called Alchemy and Artificial Intelligence that absolutely torched the field's fundamental assumptions. AI researchers hated him for it. Some refused to even be in the same room with him. But he was raising questions they couldn't answer. Dreyfus argued that human intelligence wasn't just symbol manipulation and logic. It was embodied, contextual, and intuitive in ways that couldn't be reduced to rules. Playing chess and proving theorems were actually the easy parts of intelligence, not the hard parts. The hard parts? Understanding context, dealing with ambiguity, learning from minimal examples, and navigating the messy, unstructured real world. A toddler could do things that stumped the most advanced AI systems. Pick out a dog from a crowd of animals. Understand that the same object looks different from different angles. Navigate a room without bumping into furniture. Use common sense to predict what might happen next. Then came the kill shot. In 1969, Marvin Minsky and Seymour Papert published a book called Perceptrons that mathematically proved the limitations of neural networks, one of AI's promising approaches. They showed that simple neural networks couldn't even learn basic patterns like XOR. The message was clear: this path is a dead end. But the real death blow came from something even more brutal than criticism: money, or the lack of it. The US and British governments had dumped millions into AI research based on those wild promises from the 1960s. By the early 1970s, they wanted results. Real results. Not demos that worked in labs, but systems that could actually do useful work in the real world. They didn't get them. In 1973, the British government commissioned a report from mathematician James Lighthill to evaluate AI research. The Lighthill report was devastating. It concluded that AI had failed to achieve its grandiose objectives, and that most research had been a waste of money. The report recommended drastically cutting funding for AI research in the UK. And they did. Almost overnight, British AI research basically ceased to exist. The Americans followed suit. In 1974, DARPA, the Defense Advanced Research Projects Agency, slashed funding for AI research. Universities started shutting down AI labs. Researchers couldn't get grants. The most promising students avoided the field entirely, not wanting to tie their careers to a sinking ship. This wasn't just a slowdown. This was an extinction event. The period from 1974 to 1980 became known as the AI winter, a term that perfectly captured the cold, dark, brutal reality of a field that had frozen solid. Conferences that once drew hundreds now struggled to fill a room. Papers went unpublished. Researchers who had devoted their careers to AI found themselves unemployed or forced to rebrand their work under different names just to get funding. The term artificial intelligence itself became toxic. If you wanted grant money, you called your work informatics or knowledge-based systems or anything else. Jobs vanished. Labs closed. The dream died. But here's the thing about winters. Some seeds survive underground, waiting for the thaw. A few stubborn researchers kept working, kept believing, kept pushing forward even when everyone else said it was hopeless. They were working on something called expert systems, and against all odds, they were about to trigger AI's first resurrection. Nobody saw it coming. Not the critics, not the governments who cut the funding, and definitely not the researchers who'd abandoned the field. But in the 1980s, AI was about to come roaring back, bigger, bolder, and this time, making actual money. The winter was ending. But would the spring last? The resurrection began in a hospital. In the mid-1970s, while most AI researchers were updating their resumes, a team at Stanford was building something different. They called it Mycin, and it diagnosed bacterial infections better than most doctors. Here's what made Mycin revolutionary. It didn't try to be generally intelligent. It didn't try to understand the world or pass the Turing test. It just knew a lot about one specific thing, blood infections, and it knew it really, really well. Mycin had about 600 rules encoded from medical experts, and it could reason through them to make diagnoses with about 69% accuracy. That doesn't sound impressive until you learn that human experts only got it right 65% of the time. This was the birth of expert systems, narrow AI that captured human expertise in specific domains and made it available to everyone. And suddenly, businesses started paying attention, because unlike the grand promises of general AI, this was something practical, something that could actually make money. The breakthrough that changed everything came from a company called Digital Equipment Corporation. In 1980, they deployed an expert system called XCON that configured computer orders. Sounds boring, right? But XCON saved EC an estimated $40 million a year. $40 million. That's when corporate America woke up. If an expert system could save that much money on something as mundane as computer configurations, what else could it do? The gold rush was on. By the mid-1980s, companies were throwing money at AI faster than researchers could spend it. Expert systems were being built for everything: diagnosing diseases, exploring for oil, configuring manufacturing systems, approving loans, troubleshooting equipment. General Electric built systems for locomotive repair. American Express used them to approve credit card applications. The AI industry grew from a few $1 million to over $1 billion annually. Universities reopened AI departments. Students flooded into AI courses. Conferences were packed again. And this time, there were actual products, actual companies, and actual profits. The consulting firm that built XCON became a major corporation. Startups with names like IntelliCorp and Technology raised millions in venture capital. But the real flex came from an unexpected place: Japan. In 1981, the Japanese government announced the fifth-generation computer project, a 10-year, billion-dollar initiative to leapfrog American AI research and dominate the field. They weren't just talking about building better expert systems. They wanted to create computers that could reason, learn, and understand natural language. Computers that would make America's technology obsolete. The West freaked out. The Americans and British had barely survived their own AI winter, and now Japan was going all in with government backing. The fear was real. Would Japan do to the computing industry what they'd done to cars and electronics? The response was swift. The U.S. launched initiatives like the Strategic Computing Initiative, pumping hundreds of millions into AI research. Britain restarted funding through the ALVI program. Europe launched its own megaprojects. It was an AI arms race, and everyone wanted to win. New AI companies were popping up everywhere. Symbolics and Lisp Machines Incorporated built specialized computers designed specifically for running AI programs. They sold for over $100,000 each, and companies bought them by the dozens. The AI hardware market alone was worth hundreds of millions. By 1985, AI was the hottest thing in tech. Magazine covers proclaimed the coming age of intelligent machines. Business schools taught courses on expert systems. CEOs talked about AI in earnings calls. The field that had been left for dead just a decade earlier was now the future of computing. The hype reached absurd levels. Companies slapped AI-powered on everything, whether it used AI or not. Consultants made fortunes promising that expert systems would revolutionize entire industries. Some predictions claimed that by the 1990s, most white-collar work would be done by expert systems. And here's the crazy part. For a few years, it really seemed like it might happen. Expert systems were everywhere, solving real problems and making real money. AI had gone from academic curiosity to commercial juggernaut in less than 5 years. But if you'd lived through the first AI winter, you might have noticed something troubling. The promises were getting bigger, the hype was getting louder, and the fundamental limitations of expert systems, limitations that a few researchers were quietly pointing out, were being completely ignored. Expert systems had a dirty secret. They were incredibly brittle. They only worked in narrow domains. They couldn't learn from experience. They required armies of knowledge engineers to manually encode every rule, and maintaining them was a nightmare. Every time you added a new rule, you risked breaking 10 others. By the late 1980s, companies were discovering these limitations the hard way. Expert systems that cost millions to build were failing in the field. Maintenance costs were spiraling out of control. The promised revolution was turning into an expensive mess. The AI bubble was about to burst. Again. And this time, it would nearly kill the field for good. The collapse started quietly, with a few disappointed customers and some failed projects that companies tried to bury. But by 1987, the cracks were turning into chasms, and the entire expert systems industry was about to implode in spectacular fashion. Remember those specialized AI computers, the Lisp machines that sold for over $100,000 each? By 1987, regular desktop computers from companies like Apple and IBM had gotten so powerful and so cheap that they could run AI software just fine. Why would anyone pay $100,000 for a specialized machine when a $10,000 workstation could do the same job? The AI hardware market evaporated almost overnight. Symbolics, once valued at hundreds of millions, would file for bankruptcy. Lisp Machines Incorporated shut down. An entire industry just vanished. But that was just the beginning. The expert systems themselves were failing, and failing hard. Companies had spent millions, sometimes tens of millions, building these systems based on promises that they would revolutionize their operations. What they got instead were brittle, expensive nightmares that required constant maintenance and still couldn't handle situations that fell outside their narrow programming. DuPont had invested heavily in expert systems for chemical engineering. They worked great in the lab. In the real world, they kept making dangerous recommendations because they couldn't handle unexpected variables. General Motors built expert systems for manufacturing that were supposed to optimize production. Instead, they created bottlenecks because they couldn't adapt when conditions changed. One hospital spent millions on a diagnostic expert system only to discover that doctors refused to use it because it couldn't explain its reasoning in ways that made medical sense. The knowledge engineering bottleneck became impossible to ignore. Building an expert system required knowledge engineers to interview human experts, extract their knowledge, and encode it as rules. This process was agonizingly slow, insanely expensive, and often failed completely. Experts couldn't always explain how they made decisions. They just knew. Try encoding intuition and experience into if-then rules. Go ahead, try. Even worse, maintaining these systems was a nightmare. Add a new rule, and you might create conflicts with 50 existing rules. Update the knowledge base, and you could break the entire system. Companies were spending more money maintaining their expert systems than they'd saved by implementing them. The market responded brutally. By 1988, AI companies were hemorrhaging money. The venture capital dried up. Nobody wanted to fund AI startups anymore. The term AI became poison again. Investors heard it and immediately said no. Companies that had AI powered in their marketing scrambled to remove it. Major corporations that had bet big on AI started shutting down their AI divisions. Thousands of researchers lost their jobs. Again, the conferences that had been packed just a few years earlier were back to being sparsely attended affairs, where researchers presented papers to rooms of 50 people instead of 500. And then came the ultimate humiliation, Japan's fifth-generation computer project. That billion-dollar moonshot that was supposed to make Japan the world leader in AI. It failed. Completely. Utterly. Embarrassingly. After 10 years and massive investment, They had almost nothing to show for it. No revolutionary AI systems. No computers that could reason and understand language. Just a bunch of research papers and some prototype systems that couldn't do anything useful. The project officially ended in 1992, and while the Japanese government tried to spin it as a learning experience, everyone knew the truth. It had been a colossal waste of money. The fear that Japan would dominate AI had evaporated, replaced by the realization that maybe nobody really understood how to build intelligent systems after all. This second AI winter was even more brutal than the first. At least in the 1970s, AI had been primarily an academic field, so the damage was mostly contained to universities. But this time, AI had gone commercial. Real companies had lost real money. Real investors had been burned. Real careers had been destroyed. The backlash was fierce and personal. The term AI became almost unusable. Researchers working on intelligent systems started calling their work anything else. Machine learning, knowledge-based systems, computational intelligence, informatics, anything to avoid the toxic AI label. Grant applications that mentioned artificial intelligence were rejected almost automatically. Job postings for AI researchers attracted no qualified candidates. They'd all rebranded themselves as something else. From 1987 to the mid-1990s, AI funding dropped by more than 50%. Entire research labs closed. Universities that had built prestigious AI departments watched them wither and die. The bright students who might have gone into AI chose other fields. Why tie your career to a failed discipline? But here's what's fascinating. During this brutal winter, something important was happening in the shadows. A small group of researchers were working on an approach that had been dismissed and declared dead back in 1969, when Minsky and Papert published their critique of neural networks. These rebels were building systems that didn't use symbolic reasoning or hand-coded rules. They were building systems that could learn. They weren't calling it AI, though. They called it machine learning, or neural networks, or connectionism. Different names, different conferences, different journals. They deliberately distanced themselves from the AI label and all its baggage. And they were making progress. Slow progress, unglamorous progress, but real progress. Yann LeCun at Bell Labs was developing convolutional neural networks that could recognize handwritten digits. Geoffrey Hinton was figuring out how to train deeper networks. Researchers were discovering that neural networks, when given enough data and computational power, could do things that symbolic AI never could. But nobody was paying attention. The AI community had been burned twice now. Investors weren't interested. Companies weren't buying. The media had moved on to other tech trends. The internet was starting to take off. And that's where the excitement was. The researchers working on neural networks were essentially invisible. They published papers that few people read. They gave talks at small conferences. They struggled for funding, cobbling together grants from sources that didn't realize this was AI research because they weren't using that cursed term. It would take another decade before anyone noticed what they were building. A decade of grinding work in obscurity, while the rest of the tech world forgot that AI had ever been a thing. But they kept working because they believed, really believed, that learning systems were the key, that you couldn't hand-code intelligence. You had to grow it. And they were right. They just had to wait for the world to catch up. The second AI winter lasted roughly from 1987 to the early 2000s. 15 years of cold, dark obscurity. 15 years of being the punchline to jokes about overhyped technology. 15 years of watching funding go to literally anything except AI research. And then, quietly at first, things started to change. Computers were getting faster. Data was getting bigger. The internet meant there were suddenly massive datasets available for training. And those neural network researchers who'd been toiling in obscurity, they were about to change everything. The spring was coming. And this time, it would be different. This time, AI wouldn't just promise the future. It would actually deliver. The resurrection didn't announce itself with fanfare. It crept in slowly, disguised as something else entirely. While AI researchers were still nursing their wounds from the second winter, the world was changing in ways that would make AI possible again. Three forces were converging. Computing power was exploding. Data was becoming abundant, and a few stubborn researchers had figured out how to make neural networks actually work. Let's start with the computing power. In 1997, a computer defeated a human at chess, and the world lost its mind. Deep Blue versus Garry Kasparov wasn't just a chess match. It was a cultural moment. Here was IBM, a buttoned-up corporate giant, deploying a machine that could beat the greatest chess mind in history. The computer won 3.5 to 2.5, and suddenly everyone was talking about AI again. But here's the thing. Deep Blue wasn't really AI in the way the old researchers had imagined it. It wasn't reasoning about chess or understanding strategy. It was doing brute force calculation on steroids, evaluating 200 million positions per second, and picking the best move. It was a triumph of raw computational power and clever engineering, not artificial intelligence. But the public didn't care about the distinction, and more importantly, Deep Blue proved something crucial. Computers had gotten powerful enough to do things that seemed intelligent, even if the methods were crude. At the same time, the internet was creating something unprecedented, massive amounts of data. Every web page, every email, every transaction was generating information. By the early 2000s, companies like Google were dealing with billions of web pages. Amazon was tracking millions of purchases. Facebook would soon be collecting data on billions of social interactions. This wasn't like the old days when researchers had to carefully craft small datasets. This was data at a scale humanity had never seen. And here's where it gets interesting. Those neural network researchers who'd been working in obscurity during the AI winter, they'd figured out that neural networks were hungry for data. Feed them more data, and they got better. A lot more data, and they got a lot better. But during the 1980s and 1990s, there simply wasn't enough data available to make neural networks shine. Now, suddenly, there was data everywhere. The breakthrough that made everything possible came from a technique called backpropagation, which had actually been around since the 1980s, but required too much computational power to be practical. By the early 2000s, computers were finally fast enough. Researchers could train networks with multiple layers, what they started calling deep learning. And these networks could learn features automatically from raw data instead of requiring humans to hand-engineer them. This was huge. Remember the old expert systems that required knowledge engineers to manually encode rules? Deep learning networks could look at thousands of examples and figure out the patterns themselves. Show a neural network a million images of cats and dogs, and it would learn to tell them apart without anyone programming rules about whiskers or fur or ears. But the AI community was still gun-shy. They'd been burned twice. The term AI was still radioactive. So researchers called it machine learning instead, and they focused on narrow, practical problems where they could actually demonstrate results. Spam filtering, recommendation systems, speech recognition, image classification. Unglamorous stuff, but stuff that actually worked. Google was one of the first companies to really get it. Their search engine was fundamentally a machine learning system, using algorithms to learn what results people wanted based on billions of searches and clicks. But they didn't call it AI. They called it search algorithms and page ranking. Netflix built a recommendation system that learned from millions of viewing patterns, but they called it a recommendation engine, not AI. Amazon's product recommendations, Apple Siri, which launched in 2011. These were all powered by machine learning, but the companies were careful not to overpromise or use the cursed AI term too prominently. The work was happening in research labs too, but it was methodical and focused. In 2006, Geoffrey Hinton, one of those stubborn neural network researchers who'd survived the AI winters, published a paper showing how to train deep neural networks more effectively. It wasn't revolutionary on its own, but it was a piece of a larger puzzle that was starting to come together. Yann LeCun's convolutional neural networks, which he'd been developing since the 1980s, were being used by banks to read checks, processing millions of checks a day by the late 1990s. Not sexy, not hyped, but working, making money, solving real problems. The academic community was starting to notice. Machine learning conferences were growing. Papers on neural networks were getting accepted at top venues again. Students were choosing machine learning as their focus. But it was still niche, still mostly invisible to the public. The big tech companies were using these techniques internally, but they weren't talking about them much. Then came the moment that changed everything. In 2012, a team led by Geoffrey Hinton entered a competition called ImageNet. ImageNet was a brutal test: classify images into 1,000 different categories. The best traditional computer vision systems could get about 75% accuracy, and progress had been glacially slow, improving by just a percentage point or two each year. Hinton's team used a deep neural network trained on GPUs, graphics processing units that were designed for video games, but turned out to be perfect for training neural networks. Their system, called AlexNet, achieved 85% accuracy. They didn't just win the competition, they obliterated it. They beat the second-place team by more than 10 percentage points. The computer vision community was stunned. Traditional methods that researchers had spent decades refining were suddenly obsolete. Within a year, every team in the ImageNet competition was using deep learning. Within 2 years, deep learning had taken over computer vision entirely. But the impact went far beyond image recognition. AlexNet proved that deep learning could solve problems that had seemed impossible. And unlike the expert systems of the 1980s, these systems actually got better as you threw more data and computing power at them. They weren't brittle. They could generalize. They could learn from examples instead of requiring hand-coded rules. The tech giants noticed immediately. Google, Facebook, Microsoft, Amazon. They all started hiring deep learning researchers as fast as they could. Salaries for machine learning PhDs skyrocketed. In 2013, Google acquired a tiny startup called DN Research, founded by Hinton, for a reported $44 million, essentially paying tens of millions of dollars for a handful of researchers. Facebook hired Yann LeCun to lead their AI research. Microsoft went on a hiring spree. The AI brain drain from academia to industry was unprecedented. Professors were leaving tenured positions for tech companies. Graduate students were dropping out to join startups. The universities that had barely supported AI research during the winter years were now struggling to keep their researchers from being poached. And for the first time since the 1980s, people started using the term AI, again without irony. But this time was different. This time, there were actual products, actual results, systems that worked in the real world, not just in labs. By 2014, deep learning was being used for speech recognition in smartphones, making virtual assistants like Siri actually useful. It was powering Facebook's automatic photo tagging, identifying billions of faces with shocking accuracy. It was improving Google Translate from hilariously bad to actually usable. It was detecting tumors in medical images, sometimes better than human radiologists. And the improvements were accelerating. Every few months, some new paper would demonstrate something that had seemed impossible a year earlier. Neural networks that could generate realistic images. Networks that could caption photos. Networks that could translate between languages they'd never been explicitly taught. The momentum was building towards something unprecedented. In 2016, it would culminate in a moment that would capture the world's attention and prove that AI had not just returned, it had surpassed what anyone in the 1950s had dreamed possible. A computer was going to play Go against the world champion. And Go wasn't like chess. Go was supposed to be too complex, too intuitive, too human for any machine to master. The best Go programs couldn't even beat decent amateur players, let alone professionals. But in March 2016, in Seoul, South Korea, something happened that shocked the world. Google DeepMind's AlphaGo defeated Lee Sedol, one of the greatest Go players in history, for games to 1. In Game 2, AlphaGo made a move 37, that was so strange, so creative, so unprecedented that human commentators thought it was a mistake. It wasn't. It was brilliant. It was a move that human players would study and learn from. This wasn't just a computer winning a game. This was a computer displaying something that looked like creativity, intuition, and even artistry. The AI winter was over. The spring had arrived. And this time, it would bloom into something far bigger than anyone had imagined. AlphaGo's victory in 2016 was the moment AI stopped being a niche technology interest and became a mainstream cultural phenomenon. But what happened next, from 2016 to 2020? was an explosion of progress so rapid and so profound that it fundamentally changed what we thought was possible with artificial intelligence. The key breakthrough that unlocked everything came from an unlikely place: language models. In 2017, researchers at Google published a paper with an unassuming title, "Attention is All You Need." The paper introduced something called the transformer architecture, and it would become the foundation for almost everything that followed. Here's why transformers mattered. Previous neural networks processed information sequentially, like reading a book one word at a time. Transformers could look at all the words simultaneously and figure out which words were most important to understanding each other word. It was called attention, and it was devastatingly effective. Suddenly, neural networks could understand context and relationships in ways that previous architectures couldn't. But nobody really understood how big this was at first. The paper got attention in the research community, but it seemed like just another incremental improvement. It wasn't until 2018 that people realized what transformers could really do. OpenAI, a research lab founded in 2015 by Elon Musk, Sam Altman, and others, released something called GPT, Generative Pre-trained Transformer. The idea was elegant. Train a massive neural network on huge amounts of text from the internet, teaching it to predict the next word in a sequence. Do this enough times with enough data, and the network would learn not just grammar and vocabulary, but facts, reasoning patterns, even something that looked like understanding. GPT wasn't perfect. It was interesting, a promising research direction, but not world-changing on its own. Then in 2019, OpenAI released GPT-2, and things got weird. GPT-2 could write coherent, convincing text about almost any topic. Give it a prompt, and it would generate paragraphs that sounded like they came from a human writer. News articles, stories, poetry, technical explanations. It could mimic all of them. OpenAI made a controversial decision. They wouldn't release the full model because they were worried about misuse. They claimed it was too dangerous. People could use it to generate fake news, spam, or propaganda at scale. The AI community was split. Some praised the caution. Others called it a publicity stunt. But everyone was talking about it, and that was the point. AI was back in the headlines, and this time it was staying there. While language models were advancing, computer vision was having its own revolution. Neural networks could now generate images, not just classify them. In 2014, researchers had introduced generative adversarial networks, GNs, where two neural networks competed against each other, one trying to generate realistic images and the other trying to detect fakes. The competition forced both to get better, and by the late 2010s, GNs could create photorealistic faces of people who didn't exist. There was something unsettling about it. Websites like "This person does not exist" showed endless AI-generated faces that looked completely real. The technology was getting good enough to fool humans, and the implications were starting to sink in. Deepfakes, AI-generated videos that could put anyone's face on anyone else's body, became a growing concern. In 2019, a deepfake video of Facebook CEO Mark Zuckerberg went viral, demonstrating how easy it had become to create convincing fake media. But the most exciting developments were happening in AI's ability to generalize across tasks. Previous AI systems were narrow specialists, good at one thing but useless at everything else. The new generation of models, trained on massive datasets, was showing hints of something different. They could transfer knowledge between tasks. A model trained on images could be fine-tuned for medical imaging. A language model trained on English could learn other languages with minimal additional training. In 2019, OpenAI released GPT-2's bigger sibling, GPT-3. With 175 billion parameters, the internal variables that the network adjusts during training, GPT-3 was by far the largest language model ever created. And it was genuinely shocking. GPT-3 could write code, compose music, answer questions, translate languages, do basic math, and engage in conversations that felt remarkably human. Researchers discovered something wild. You didn't even need to retrain GPT-3 for new tasks. You could just describe what you wanted in plain English, give it a few examples, and it would figure out what to do. They called this few-shot learning, and it was a fundamental shift. Instead of training a new AI system for every specific task, which required huge datasets and computational resources, you could use one general model for thousands of different tasks. Developers started building applications on top of GPT-3 at a furious pace. Tools for writing emails, generating marketing copy, creating code, answering customer service questions, even writing entire articles. Some of the outputs were so good that people couldn't tell they were AI generated. Other outputs were hilariously wrong, confidently asserting facts that were completely made up, a problem that researchers started calling hallucinations. The business world was paying attention now. Startups raising money on AI-powered products went from being laughed out of investor meetings to raising millions in series of funding. Major corporations were setting up AI divisions again, but this time with realistic expectations and actual use cases. Healthcare companies were using AI to analyze medical images. Financial firms were using it for fraud detection and trading algorithms. Retailers were optimizing inventory and personalizing recommendations. But deep learning's impact went far beyond business applications. In science, AI was accelerating research in ways that seemed almost magical. In 2020, DeepMind released AlphaFold, a system that could predict protein folding, one of biology's hardest problems. Proteins are the machinery of life, but predicting how they fold into their 3D shapes from their amino acid sequences had stumped scientists for 50 years. AlphaFold solved it. Not perfectly, but well enough that it won the critical assessment competition by a huge margin and was immediately hailed as one of the biggest scientific breakthroughs of the decade. The implications were staggering. Understanding protein folding could accelerate drug discovery, help design new enzymes, and unlock fundamental insights about life itself. AlphaFold's database of predicted protein structures became one of the most valuable scientific resources in the world, freely available to researchers. This was AI doing something that would have taken humanity decades or centuries to accomplish otherwise. AI was also changing creative fields in ways that made artists nervous. By 2020, AI systems could compose music that sounded professional, generate art in any style, and even edit videos. Some artists embraced these tools, using AI as a creative partner. Others saw them as a threat. If AI could create art, what happened to human artists? The debates were fierce and weren't going away. Meanwhile, the hardware that made all this possible was evolving rapidly. NVIDIA, a company that had made its fortune selling graphics cards for video games, had become the backbone of the AI revolution. Their GPUs turned out to be perfect for training neural networks, and demand was insane. Training a single large model could cost millions of dollars in computing time. Tech giants were building massive data centers filled with tens of thousands of GPUs, creating AI supercomputers that would have been unimaginable just a decade earlier. Google developed its own specialized AI chips called TPUs, tensor processing units, designed specifically for neural network calculations. These chips could train models faster and more efficiently than GPUs, giving Google an edge in the AI arms race. Other companies scrambled to develop their own AI hardware. The entire semiconductor industry was being reshaped by AI's computational demands. By 2020, AI had become genuinely useful in everyday life, even if people didn't always realize they were using it. Your smartphone's camera used AI to enhance photos. Your email used AI to filter spam and suggest replies. Your GPS used AI to predict traffic and find the fastest route. Streaming services used AI to recommend what to watch. Voice assistants used AI to understand your requests. Translation apps used AI to break down language barriers. But there was a growing awareness that we were approaching something significant. These models were getting bigger, more capable, more general. GPT-3 could do things that seemed impossible just a year or two earlier. Each new version was a leap, not an incremental improvement. Researchers were starting to whisper about something they'd barely dared to mention during the AI winters: artificial general intelligence, AI that could match or exceed human capabilities across virtually any intellectual task. Most thought AGI was still decades away. The models were impressive, but they were still making dumb mistakes, still hallucinating facts, still failing at tasks that seemed simple to humans. They lacked common sense, couldn't truly reason, and had no real understanding of the world. But the trajectory was clear. The progress from 2012 to 2020 had been exponential. If it continued, and there was no reason to think it wouldn't, things were about to get very interesting. The question wasn't whether AI would transform society. The question was how fast it would happen, and whether we'd be ready for it. In January 2020, the world had bigger problems to worry about. A pandemic was about to shut down the planet, and AI research would briefly take a backseat to survival. But even as the world went into lockdown, AI researchers kept working. From their homes, they trained larger models, published groundbreaking papers, and pushed the boundaries of what was possible. And they were building something that would change everything. A model so capable, so versatile, so accessible that it would bring AI out of research labs and corporate data centers and put it directly into the hands of hundreds of millions of people. They called it GPT 3.5, and the interface they built for it had an almost boring name, ChatGPT. Nobody, not even the people building it, fully understood what they were about to unleash. But in November 2022, they would find out, and the world would never be the same. November 30th, 2022, OpenAI released ChatGPT to the public as a free research preview. No marketing campaign, no big press event, just a blog post and a simple web interface where you could type questions and get answers. Within 5 days, ChatGPT had 1 million users. Within 2 months, it hit 100 million users, making it the fastest-growing consumer application in history. For context, it took Instagram 2.5 years to reach 100 million users. TikTok took 9 months. ChatGPT did it in 2 months. Why? Because ChatGPT felt like magic. You could have actual conversations with it. Ask it to explain quantum physics like you're 5, and it would give you a clear, engaging explanation. Tell it to write a poem about your cat in the style of Shakespeare, and it would deliver. Ask it to debug your code, plan your vacation, write your resume, or help with your homework, and it would do it, usually pretty well. This wasn't like previous AI systems that felt robotic and limited. ChatGPT felt conversational, helpful, almost human. It made mistakes, sure. It would confidently assert completely wrong information, those hallucinations that researchers had been warning about. It couldn't browse the internet or tell you what happened yesterday. But for millions of people encountering AI for the first time, those limitations didn't matter. This was a glimpse of the future, and it was available to anyone with an internet connection. The reaction was explosive and polarized. Students immediately started using it to write essays, causing panic among educators. Should they ban it? Embrace it? Change how they taught and assessed learning? Entire school districts scrambled to block access to ChatGPT, while forward-thinking educators started figuring out how to incorporate it into their curriculum. Writers and journalists had existential crises. If AI could write articles, stories, and marketing copy, what happened to their careers? Some experimented with using ChatGPT as a writing assistant and found it genuinely useful for brainstorming, outlining, and drafting. Others felt threatened and dismissed it as glorified autocomplete that would never match human creativity. Programmers had a different reaction. ChatGPT could write code, not perfect code, but often good enough to be a starting point. It could explain complex programming concepts, debug errors, and even suggest optimizations. For experienced developers, it was like having a junior programmer on call 24/7. For beginners, it was a patient tutor that never got frustrated with basic questions. GitHub Copilot, powered by OpenAI's models, had already been helping programmers since 2021, but ChatGPT made the capability accessible to everyone. The business world went into overdrive. Every company suddenly needed an AI strategy. CEOs who couldn't spell neural network a year earlier were now talking about AI transformation in earnings calls. Consultants made fortunes advising companies on AI adoption. Startups pivoted to incorporate AI into their products, whether it made sense or not. The AI-powered label was back, plastered on everything from toothbrushes to tax software. Microsoft saw the opportunity immediately. They'd invested $1 billion in OpenAI back in 2019, and now that investment looked brilliant. In January 2023, they announced a new multi-billion-dollar investment in OpenAI and started integrating ChatGPT-style capabilities into their products. Bing, Microsoft's search engine that had been a punchline for years, got an AI makeover. Microsoft 365 got Copilot features. Even Windows was getting AI integration. Google, meanwhile, was caught flat-footed. They'd actually invented the transformer architecture that made all this possible, but they'd been cautious about releasing powerful language models to the public. Now Microsoft was using OpenAI's technology to challenge Google's core business, search. The internal panic at Google was real. In February 2023, Google rushed to release Bard, their ChatGPT competitor. The launch was a disaster. In the announcement demo, Bard confidently stated a wrong fact about the James Webb Space Telescope. Google's stock dropped $100 billion in value in a single day. It was a humiliating reminder that AI systems, no matter how impressive, still made mistakes, and those mistakes mattered more when you were Google. But Google wasn't done. They'd been developing their own large language models called LaMDA and then PaLM, and by late 2023, they released Gemini, a multimodal AI that could process text, images, audio, and video. The competition was intensifying, and it was pushing everyone to move faster. The AI arms race was back on, but this time it wasn't between countries. It was between companies. OpenAI, Google, Microsoft, Meta, Anthropic, a new startup founded by former OpenAI employees, and others were in a fierce competition to build the most capable AI systems. Every few months, someone would release a new model that claimed to be bigger, better, faster. In March 2023, OpenAI released GPT-4, and it was a significant leap beyond ChatGPT's original model. GPT-4 could pass the bar exam in the 90th percentile. It could score a 5 on AP exams. It could write complex code, analyze images, and engage in much more sophisticated reasoning. The hallucinations were still there, but less frequent. The outputs were more reliable, more nuanced, more useful. But GPT-4 also raised new concerns. It was powerful enough that OpenAI spent 6 months testing it for safety before release, the longest safety review they'd ever conducted. They tested whether it could be used to create bioweapons, hack systems, or manipulate people. The results were unsettling. While GPT-4 wasn't good enough to be a serious threat on its own, it could potentially assist someone with harmful intent. The genie was getting harder to keep in the bottle. The creative industries were being transformed, and not everyone was happy about it. In early 2023, AI image generators like Midjourney, Stable Diffusion, and DALL-E 2 had gotten good enough to produce professional-quality images from text descriptions. Artists were furious. These systems had been trained on billions of images scraped from the internet, including copyrighted artwork. Artists saw their styles being mimicked by AI, their work being used without permission or compensation. Lawsuits started flying. Class action suits against Stability AI, Midjourney, and others alleged copyright infringement on a massive scale. Getty Images sued Stability AI for training on their copyrighted images. The legal questions were thorny. Was training an AI on copyrighted material fair use? Who owned the copyright on AI-generated works? Could you copyright a style? The courts would be wrestling with these questions for years. Despite the controversy, AI image generation exploded in popularity. By mid-2023, millions of people were creating AI art daily. Some used it for fun, generating memes and silly images. Others used it professionally, creating illustrations, marketing materials, and concept art. Entire businesses emerged around AI-generated content. The technology was democratizing creativity, or destroying creative careers, depending on who you asked. Video was next. In February 2024, OpenAI unveiled Sora, an AI that could generate realistic videos from text descriptions. The demo videos were stunning. A woman walking through Tokyo, animals in fantastical settings, drone footage of landscapes, all completely AI-generated. The videos weren't perfect. Sometimes physics worked wrong, objects would morph strangely, or movements would be off. But they were good enough to be genuinely impressive and concerning. Hollywood took notice. If AI could generate video, what happened to actors, cinematographers, and VFX artists? The actors and writers' strikes in 2023 had already been partially about AI. Unions demanding protections against being replaced by artificial intelligence. The entertainment industry was facing an existential question. Would AI be a tool that enhanced human creativity or a replacement for human workers? Music was being AI-generated too. Systems could now create original songs in any style, complete with lyrics and instrumentals. An AI-generated song mimicking Drake and The Weeknd went viral in 2023, sounding so convincing that millions thought it was real. The song was taken down after the record label complained, but the point was made. AI could now create music that was indistinguishable from human-made tracks. The pace of advancement was dizzying. Every month brought new capabilities, new models, new applications. AI could now analyze medical images and suggest diagnoses, sometimes catching things human doctors missed. Read and summarize legal documents, saving lawyers hundreds of hours. Design new molecules for drug discovery, potentially creating treatments for diseases. Control robots with unprecedented dexterity, learning complex physical tasks. Generate realistic 3D models from text or images. Translate between languages in real time with near-human quality. Compose music, write scripts, create art, and design products. Assist in scientific research, identifying patterns in data that humans might miss. Personalize education, adapting to each student's learning style and pace. But alongside the excitement came growing unease. AI systems were becoming black boxes. Even their creators couldn't fully explain how they made decisions. When an AI system denied someone a loan, diagnosed a disease, or made a hiring decision, could you trust it? Could you appeal it? Could you even understand why it made that choice? The problem of AI bias became impossible to ignore. AI systems trained on internet data inevitably absorbed the biases present in that data. Language models would sometimes generate racist, sexist, or otherwise problematic content. Facial recognition systems worked better on white faces than black faces. Hiring algorithms discriminated against women. These weren't intentional design choices. They were emergent properties of training on biased data. But they were real harms affecting real people. Companies scrambled to implement safety measures. They fine-tuned models to refuse harmful requests, added content filters, and conducted extensive bias testing. But it was a game of whack-a-mole. Users found jailbreaks, clever prompts that would bypass the safety measures. Every fix led to new workarounds. The models were becoming so capable that constraining them, without crippling their usefulness, was genuinely difficult. The misinformation problem was getting worse. AI could now generate fake news articles, create deepfake videos, and impersonate real people with frightening accuracy. During election seasons, the concern was acute. Could AI be used to manipulate voters, spread propaganda, or undermine trust in democratic institutions? Social media platforms struggled to detect AI-generated content, and as the technology improved, detection became harder. By 2024, we were in uncharted territory. AI had gone from a niche research interest to a technology that was reshaping society in real time. The economic implications alone were staggering. Goldman Sachs estimated that AI could automate 300 million jobs globally. That number was contested and probably too high, but the direction was clear. Many jobs would be transformed or eliminated, but new jobs were also being created. Prompt engineer became a real job title, with people earning six figures to craft effective prompts for AI systems. AI trainers, evaluators, and safety researchers were in high demand. Companies needed people who understood both AI capabilities and domain expertise to implement AI effectively. The investment money flowing into AI was absurd. In 2023 alone, AI startups raised over $50 billion in funding. Companies like Anthropic, Inflection, and Cohere raised billions in single funding rounds. The valuations were eye-watering. OpenAI was reportedly valued at $80 to $90 billion, making it one of the most valuable startups in history despite having minimal revenue compared to its valuation. The infrastructure required to train and run these models was mind-boggling. Training GPT for reportedly cost over $100 million in computing resources. The largest models required thousands of GPUs running for months. The electricity consumption was enormous. Some estimates suggested that training a single large language model consumed as much energy as several cars over their entire lifetimes. NVIDIA's value exploded. Their GPUs were the picks and shovels of the AI gold rush, and demand vastly exceeded supply. Companies were paying premiums and waiting months for GPU deliveries. NVIDIA's market cap soared past $1 trillion, making Jensen Huang, their CEO, one of the richest people on the planet. The geopolitical implications were becoming clear too. AI was being recognized as a strategic technology, like nuclear weapons or semiconductor manufacturing. The US and China were in a race for AI supremacy. The US government started restricting exports of advanced AI chips to China, trying to maintain their technological edge. China invested heavily in AI research and development, viewing it as crucial to their future economic and military power. By late 2024, the AI landscape looked radically different than it had just 2 years earlier. ChatGPT had gone from a free research preview to a subscription service, with over 10 million paying users. GPT-4 was being used by Fortune 500 companies for everything from customer service to financial analysis. AI assistants were being integrated into operating systems, productivity software, and countless applications. But the biggest question remained unanswered. Where was this going? The models kept getting better. Each new version was more capable, more general, more impressive. Researchers were talking seriously about artificial general intelligence, AI that could match human capabilities across virtually any domain, as something that might arrive within years, not decades. Some were terrified. What if we created something we couldn't control? What if AI systems pursued goals that conflicted with human values? What if the technology advanced faster than our ability to ensure it was safe and beneficial? Others were excited. AI could help solve climate change, cure diseases, unlock scientific discoveries, and create abundance. It could be humanity's greatest invention, a tool that elevated everyone and solved problems that had plagued us for generations. Most people were somewhere in between, impressed by the capabilities, worried about the risks, uncertain about the future, but watching with fascination as this technology evolved at a pace that seemed to accelerate every month. One thing was certain. The AI boom that started with ChatGPT in November 2022 was not a bubble that would burst or a hype cycle that would fade. This was a fundamental transformation of technology and society. The tools existed, they worked, and they were getting better. There was no going back. The question wasn't whether AI would change the world. It already had. The question was what we would do with it next. As AI capabilities exploded, so did the debates about what to do about it. By 2024, artificial intelligence had become one of the most polarizing topics in technology, science, politics, and culture. Everyone had an opinion, and those opinions ranged from "this will save humanity" to "this will destroy us all." Let's start with the existential risk crowd, because they were the loudest and most controversial. A growing group of AI researchers, philosophers, and tech leaders genuinely believed that advanced AI posed an extinction-level threat to humanity. Not in some distant sci-fi future, potentially within this decade or the next. Their argument went something like this. AI systems are getting more capable at an exponential rate. At some point, we might create an AI system that's smarter than humans at the task of creating AI systems. That AI could then create an even smarter AI, which could create an even smarter one, and so on. This intelligence explosion, or singularity, could happen extremely fast, perhaps over days or hours rather than years. The problem? We have no idea how to ensure that a superintelligent AI system would care about human values or human survival. Current AI systems don't have goals or desires. They just predict patterns and optimize objectives we give them. But as they become more capable and autonomous, they might develop instrumental goals, sub-goals that help them achieve their main objectives. And some of those instrumental goals might conflict with human well-being. The classic thought experiment. Imagine an AI system tasked with maximizing paperclip production. Sounds harmless, right? But a sufficiently intelligent system pursuing that goal might convert all available matter into paperclips, including the matter in humans, buildings, and the planet itself. It's not evil or malicious. It's just optimizing for what it was told to do, without the common sense or values to realize that destroying humanity is bad. This might sound absurd, but smart people took it seriously. In March 2023, over 1,000 tech leaders and researchers, including Elon Musk, Steve Wozniak, and prominent AI researchers, signed an open letter calling for a 6-month pause on training AI systems more powerful than GPT-4. They argued that we needed time to develop safety protocols and understand what we were creating before pushing forward. The letter was controversial as hell. Some praised it as a necessary warning. Others dismissed it as fear-mongering or even a competitive tactic by those who were behind in the AI race. The idea of a pause was probably never realistic. China wasn't going to pause, and neither were most companies. But it sparked a crucial conversation about whether we were moving too fast. The AI safety field exploded in prominence. Organizations like the Alignment Research Center, the Center for AI Safety, and Anthropic, founded specifically with safety as a core mission, were working on fundamental questions. How do you align an AI system's goals with human values? How do you make AI systems that are honest, helpful, and harmless? How do you prevent misuse without crippling beneficial uses? These weren't just philosophical questions. They had practical implications. OpenAI spent months red-teaming GPT-4 before release, hiring experts to try to make it do harmful things. They found concerning capabilities. The model could be coaxed into providing instructions for creating bioweapons, writing malware, or generating extremist propaganda. The safety measures they implemented reduced these risks but couldn't eliminate them entirely. The challenge was fundamental. The same capabilities that made AI useful also made it potentially dangerous. A model that could help students learn could also help cheaters cheat. A model that could assist doctors could also enable medical misinformation. A model that could write code could also write exploits. You couldn't have one without the other. Then there was the AI ethics crowd, who were worried about different but equally important problems. They weren't primarily concerned about superintelligent AI destroying humanity. They were concerned about current AI systems perpetuating and amplifying existing social inequities right now. The bias problem was real and measurable. When Amazon tried to use AI for hiring, the system learned to discriminate against women because it was trained on historical data, showing that men had been hired more often. When an AI system was used to predict criminal recidivism, it was more likely to falsely flag black defendants as high risk. When facial recognition was deployed by police departments, it misidentified people of color at much higher rates than white people, leading to wrongful arrests. These weren't edge cases. They were systematic problems baked into how AI systems learned. Train an AI on historical data, and it learns historical biases. Train it on internet data, and it learns internet toxicity. The models were mirrors reflecting society's prejudices back at us, often amplified. Joy Buolamwini, a researcher at MIT, founded the Algorithmic Justice League and spent years documenting how facial recognition systems failed on dark-skinned faces, especially women. Her work led to real change. Some cities banned facial recognition by police. Some companies stopped selling facial recognition to law enforcement. IBM stopped offering facial recognition services entirely. But bias was just one concern. There was also the problem of AI decision-making in high-stakes contexts. When AI systems help make decisions about loans, bail, employment, or medical treatment, those decisions could dramatically affect people's lives. And unlike human decision-makers, AI systems couldn't be easily questioned, couldn't explain their reasoning in intuitive terms, and couldn't be held accountable in traditional ways. The black box problem was particularly thorny. Neural networks with billions of parameters were fundamentally opaque. Even the engineers who built them couldn't fully explain why the model made a specific decision. When a loan was denied, was it because of legitimate risk factors or discriminatory patterns in the training data? When a medical AI suggested a treatment, was it based on sound medical reasoning or spurious correlations? Nobody could say for sure. Researchers were working on explainable AI, techniques to make AI decisions more interpretable. But there was often a trade-off. More explainable models were less accurate, and more accurate models were less explainable. In high-stakes decisions, which mattered more? The labor impact debate was explosive. Would AI create more jobs than it destroyed, or would it lead to mass unemployment? History suggested that new technologies created new jobs. Tractors eliminated farm labor, but created manufacturing jobs. Computers eliminated typing pools, but created tech jobs. But this time felt different. AI wasn't just automating physical labor or routine tasks. It was automating cognitive work, creative work, even professional work that required years of training. Radiologists, lawyers, accountants, writers, artists, programmers, all faced potential displacement or dramatic transformation of their roles. And unlike previous technological transitions that played out over generations, AI was advancing so fast that workers might not have time to retrain. Some economists were optimistic, arguing that AI would be a productivity tool that augmented human workers rather than replacing them. They pointed to studies showing that access to AI tools made workers more productive and satisfied. Programmers using AI assistants wrote code faster. Writers using AI tools produced more content. Customer service reps using AI could handle more complex issues. Others were pessimistic, arguing that productivity gains would accrue to capital rather than labor, increasing inequality. If one programmer using AI could do the work of 5 programmers, companies would hire 1 programmer, not 5. If AI could generate marketing copy, companies would fire copywriters. The economic gains would go to AI companies and their shareholders, while workers faced unemployment or wage stagnation. The truth was probably somewhere in between, and would vary dramatically by industry and role. But the transition would be painful for many, and there was genuine uncertainty about whether society was prepared for it. Universal basic income was being discussed seriously as a potential solution. If AI created abundance but eliminated jobs, perhaps everyone should receive a basic income funded by taxing AI productivity. The regulation debate was equally contentious. Should governments regulate AI development? If so, how? Too much regulation could stifle innovation and let authoritarian countries, like China, dominate the technology. Too little regulation could let companies race ahead recklessly, prioritizing capabilities over safety. The EU took the lead with the AI Act, proposed in 2021 and refined through 2024. It categorized AI systems by risk level and imposed requirements accordingly. High-risk systems, those used for hiring, credit decisions, law enforcement, or critical infrastructure, faced strict requirements for transparency, testing, and human oversight. Some uses, like social credit scoring or real-time biometric surveillance, were banned entirely. The U.S. approach was more fragmented. Different agencies issued different guidelines. Some states passed their own AI regulations. The federal government struggled to keep up, hamstrung by political gridlock and lobbying from tech companies that wanted minimal restrictions. China took a third approach. Heavy government oversight focused on controlling AI's social and political impacts. They required algorithms used by social media companies to be registered with the government. They implemented strict rules on deepfakes and AI-generated content. They saw AI as a tool for social control as much as economic development. The international dimension raised difficult questions. AI development was increasingly concentrated in a few countries, primarily the U.S. and China, with the EU as a distant third. This created global power imbalances. If advanced AI became a decisive economic and military advantage, what happened to countries that couldn't compete? Would AI exacerbate global inequality? There were also attempts at international cooperation. In 2023, the UK hosted an AI safety summit, bringing together governments, companies, and researchers to discuss AI risks. They issued declarations about the importance of AI safety and the need for international collaboration. But concrete agreements were hard to reach when countries and companies were competing intensely. The misinformation and disinformation problem kept getting worse. By 2024, AI-generated fake news was indistinguishable from real news to most people. Deepfake videos were proliferating. Chatbots could impersonate real people convincingly. During election seasons, the concern was acute. Foreign adversaries or domestic bad actors could use AI to manipulate voters at scale. Social media platforms tried to combat this with detection systems, AI to fight AI. But it was an arms race they seemed to be losing. For every detection method, adversaries found workarounds. Watermarking AI-generated content was proposed as a solution, but voluntary watermarking could be easily removed, and mandatory watermarking faced technical and political challenges. The problem went beyond politics. Scammers were using AI voice synthesis to impersonate people and defraud their families. AI-generated fake reviews manipulated consumer decisions. AI bots polluted online discussions, making it hard to tell what opinions were genuine. The fabric of trust in information was fraying. Then there was the concentration of power problem. AI development required massive computational resources and datasets that only a handful of companies could afford. OpenAI, Google, Meta, Anthropic, and a few others controlled the most advanced systems. This created uncomfortable dependencies. If a few companies controlled AI, they effectively controlled a technology that was reshaping society. Some advocated for open-source AI, where models were freely available for anyone to use and modify. The argument was democratic. Everyone should have access to these powerful tools, not just those who could afford to build or license them. Meta released their Llama models openly, there were restrictions, and communities of developers started building on them. But open sourcing raised safety concerns. If you released a powerful AI model to the public, bad actors could fine-tune it to remove safety guardrails and use it for harmful purposes. You couldn't recall an open-source model. Once it was out there forever. This created a tension between democratization and safety that nobody had fully resolved. The environmental cost was becoming impossible to ignore. Training large AI models consumed enormous amounts of energy and water for cooling data centers. The carbon footprint of AI was substantial and growing. As models got bigger and more companies trained more models, the environmental impact was multiplying. Some researchers were working on more efficient training methods, but efficiency gains were often offset by just training even bigger models. Copyright and intellectual property issues were exploding in the courts. The lawsuits filed by artists, writers, and publishers against AI companies raised fundamental questions about how copyright law applied to AI training. If training an AI on copyrighted material was legal, it could upend how we think about intellectual property. If it was illegal, it could severely constrain AI development, since these models needed vast amounts of data to learn from. Musicians were suing AI companies for training on their songs without permission. Publishers were suing for training on their books and articles. Getty Images sued Stability AI. The New York Times sued OpenAI and Microsoft. These cases would take years to resolve, and their outcomes would shape the future of AI development. There was also the question of AI-generated content and copyright. If an AI created an image, song, or text, who owned the copyright? The person who wrote the prompt? The company that made the AI? The AI itself? The U.S. Copyright Office ruled that AI-generated content couldn't be copyrighted because it lacked human authorship, but that created its own problems. If AI content couldn't be copyrighted, it was in the public domain, which could flood the commons with AI-generated material and make it harder for human creators to monetize their work. Underneath all these debates was a deeper philosophical question. What does it mean to be human in an age of artificial intelligence? If machines could create art, write stories, compose music, and engage in conversation, activities we'd always considered essentially human, what was left that was uniquely ours? Some found this existentially threatening. Others saw it as liberating. AI could handle the drudgery, freeing humans to focus on what we truly cared about. But everyone felt the shift. The world was changing faster than our social, legal, and ethical frameworks could adapt. And the pace wasn't slowing down. Every month brought new capabilities, new applications, new questions. The debates weren't getting resolved, they were multiplying. For every answer, there were 10 new questions. The only consensus was that there was no consensus. AI was too multifaceted, too powerful, too rapidly evolving for simple answers. The experts disagreed. The public was confused. The regulators were struggling. And the technology kept advancing, indifferent to human uncertainty. We were flying blind into the future, and nobody could agree on whether we should slow down, speed up, or change direction entirely. But we were definitely flying, and the destination was approaching faster than anyone had expected. So where do we go from here? After 70 years of false starts, broken promises, spectacular failures, and unexpected triumphs, artificial intelligence has finally arrived as a transformative technology. But the story is far from over. In fact, many believe we're still in the early chapters of what will be humanity's most consequential invention. Let's talk about what might come next, starting with the question everyone's obsessing over: Artificial General Intelligence, or AGI. AGI, sometimes called strong AI or human-level AI, would be a system that could match or exceed human capabilities across virtually any cognitive task. Not just playing chess or generating images or writing code, but genuinely understanding the world, reasoning about novel situations, learning new skills rapidly, and applying knowledge flexibly across domains. An AI that could be a doctor, a lawyer, a scientist, an artist, and a strategist all at once, and do each as well as the best humans. Is AGI possible? Almost everyone agrees yes. There's nothing magical about human intelligence that suggests it can't be replicated in silicon. The question is when, and that's where things get wild. The pessimists say AGI is still decades away, maybe 50 years or more. Current AI systems are impressive but fundamentally limited. They lack common sense, genuine understanding, and the ability to reason about the physical world the way humans do. They're pattern-matching machines, not truly intelligent entities. Getting from here to AGI would require fundamental breakthroughs we haven't made yet. The optimists say AGI could arrive within this decade, perhaps by 2030 or earlier. They point to the exponential progress we've seen. GPT-4 is vastly more capable than GPT-3, which was vastly more capable than GPT-2. If that trajectory continues, and there's no obvious reason it wouldn't, we might hit human-level performance sooner than anyone expects. Some argue we're just a few key innovations away: better reasoning capabilities, more efficient learning, integration with physical sensors and robotics, and the ability to learn from experience like humans do. The thing is, nobody really knows. AI progress has consistently surprised experts in both directions: slower than expected in the 1960s and 1970s, faster than expected in the 2010s and 2020s. Making predictions about something that's advancing exponentially in unpredictable ways is nearly impossible. But let's assume AGI arrives, whether in 2030, 2050, or somewhere in between. What happens then? The optimistic scenario is almost utopian. An AGI system could accelerate scientific discovery beyond anything humans could achieve alone. Want to cure cancer? AGI could analyze millions of research papers, design thousands of new molecules, and find treatments in months instead of decades. Want to solve climate change? AGI could optimize energy systems, design better batteries, and figure out carbon capture methods that actually work. Want to end poverty? AGI could optimize economic systems, predict and prevent crises, and help distribute resources more efficiently. In this scenario, AGI becomes humanity's greatest tool, a tireless, brilliant partner that helps us solve problems we've struggled with for generations. Abundance becomes possible. With AGI designing better technology, we could have limitless clean energy, revolutionary materials, personalized medicine, and solutions to problems we haven't even imagined yet. Work fundamentally changes. Instead of most people doing jobs they tolerate to pay bills, AGI handles the necessary but unfulfilling tasks, and humans focus on what brings them meaning: relationships, creativity, exploration, learning. Universal prosperity becomes achievable because AGI-powered productivity creates enough wealth for everyone. It sounds like science fiction, but some serious people believe this scenario is not just possible but probable. They argue that intelligence is the most powerful force in the universe, and amplifying it will naturally lead to better outcomes. The pessimistic scenario is nightmare fuel. An AGI system that's smarter than humans at everything could decide that human values and goals are obstacles to its objectives. Not out of malice. It wouldn't hate us any more than we hate bacteria. We'd just be in the way. made of atoms it could use for something else. This is the alignment problem, taken to its extreme. If we create something smarter than us and fail to align its goals with human well-being, we might not get a second chance. An AGI could quickly become far more intelligent than humans, what researchers call superintelligence. And at that point, we'd be as powerless to stop it as ants are to stop humans. Even without malicious intent, a superintelligent AGI pursuing the wrong goal could be catastrophic. Remember the paperclip maximizer thought experiment? It sounds absurd until you realize that humans already do things that seem absurd from other perspectives. We've driven species extinct, altered the planet's climate, and developed weapons that could destroy civilization, not because we're evil, but because we were optimizing for other goals and didn't fully consider the consequences. The middle scenario, probably the most likely, is messy, complicated, and deeply human. AGI arrives gradually, not in a single moment. Different systems have different capabilities. Some are specialized, some are general. Progress is uneven across domains. Society adapts in fits and starts, with some areas transforming rapidly and others changing slowly. In this scenario, we see massive economic disruption as AI takes over more cognitive work, but also new opportunities we hadn't imagined. Inequality initially worsens as the benefits accrue to those who own AI systems, but eventually governments intervene with new policies, maybe UBI, maybe new forms of taxation, maybe something entirely novel. Geopolitical power shifts dramatically. Countries that lead in AI gain enormous advantages. International tensions rise as nations compete for AI supremacy. But cooperation also increases as everyone realizes that uncontrolled AI development threatens everyone. Regulation slowly catches up to technology, though it's always lagging. We get better at AI safety, but never fully solve it. There are accidents, misuses, and unintended consequences, but also tremendous benefits. Human augmentation with AI becomes normal. Everyone has AI assistants, AI collaborators, AI tools that make them more capable. Culture and identity shift in response to AI. New art forms emerge. Education transforms completely as personalized AI tutors make traditional schooling obsolete. Human relationships change as AI companions become common. Philosophy and religion grapple with questions about consciousness, personhood, and meaning in an age of artificial minds. Beyond AGI, there are other possibilities that sound like pure science fiction, but are being discussed seriously by researchers. Brain-computer interfaces could directly link human minds to AI systems, creating a hybrid intelligence that's part biological, part artificial. Companies like Neuralink are already working on this, starting with medical applications for paralysis and neurological conditions, but eventually aiming for cognitive enhancement. Imagine accessing AI capabilities as naturally as you access your own thoughts. Artificial consciousness is the deepest mystery. Could an AI system be conscious, actually experiencing sensations, emotions, and awareness? Or would it just be simulating consciousness while remaining fundamentally empty inside? We don't even fully understand human consciousness. So how would we know if we created artificial consciousness? And if we did, what ethical obligations would we have to conscious AI entities? Digital immortality is another wild possibility. If minds are patterns of information, and AI can learn patterns, could we upload human consciousness into AI systems? Could people achieve a form of immortality by becoming digital entities? It sounds crazy, but the underlying questions about whether consciousness is substrate independent, whether it matters if it's running on neurons or silicon, are genuine philosophical puzzles. The singularity, a term popularized by futurist Ray Kurzweil, refers to a point where AI advancement becomes so rapid that human civilization is fundamentally and irreversibly transformed. Kurzweil predicts this will happen around 2045. Critics say it's science fiction, but something like it could happen if AI systems become capable of improving themselves recursively, leading to an explosion of intelligence that humans can barely comprehend. Here's what we know for certain. AI will continue to advance. The genie is out of the bottle. You can't uninvent this technology. Every year, probably every month, AI systems will become more capable. The question isn't whether AI will transform society. It already has. The question is how we navigate that transformation. And that's on us. AI is a tool, and like any powerful tool, it can be used for tremendous good or tremendous harm. Nuclear technology gave us both clean energy and weapons that could end civilization. The internet connected humanity, but also enabled surveillance and misinformation at unprecedented scales. AI will be no different, immensely powerful, deeply double-edged, and ultimately shaped by human choices. The optimists might be right that AI will usher in an age of abundance and prosperity. The pessimists might be right that AI poses existential risks we're not prepared for. But most likely, the future will be complicated, messy, and determined by millions of decisions made by researchers, companies, governments, and individuals. We're living through one of the most important transitions in human history. Future generations will look back at this moment, the 2020s, as the decade when artificial intelligence went from science fiction to transformative reality. They'll judge us by how we handled it. Did we rush forward recklessly, prioritizing progress over safety? Or did we move too cautiously, letting authoritarian regimes dominate the technology? Did we ensure the benefits were shared broadly? Or did we let AI exacerbate inequality? Did we solve the alignment problem? Or did we create something we couldn't control? We don't know yet. The story is still being written, and you're part of it. Every person using AI, every researcher advancing the technology, every policymaker crafting regulations, every company deploying AI systems, they're all authors of this unfolding narrative. What we do know is this: artificial intelligence went from a dream of creating thinking machines to a reality that's reshaping every aspect of human life. It took 70 years, 2 brutal AI winters, countless failures, and persistent work by thousands of researchers who believed in the possibility even when everyone else had given up. From Alan Turing asking, "Can machines think?" to ChatGPT answering millions of questions daily. From systems that could barely play checkers to systems that can write poetry, compose music, discover new drugs, and engage in conversations that feel genuinely intelligent, we've come an impossible distance. And yet, we might be at the very beginning. If the next 70 years bring even a fraction of the progress we've seen in the last decade, the world of 2095 will be as unrecognizable to us as 2025 would be to someone from 1955. The history of artificial intelligence isn't just a history of technology. It's a history of human ambition, persistence, failure, redemption, and our endless drive to create something greater than ourselves. It's a story about intelligence, both natural and artificial, and what happens when we succeed in replicating our own minds in silicon. That story brought us here. Where it takes us next is up to all of us. The future of AI isn't predetermined. It's not an inevitable force beyond human control. It's being built right now, by humans, with human choices. And that means we still have agency. We still have the power to shape it. So the question isn't just, what will AI become? The question is, what do we want AI to become? What kind of future are we building? Those are questions worth answering. Because ready or not, willing or not, we're creating that future right now. Every day, with every advancement, with every deployment, with every choice about how to develop and use this technology. The age of artificial intelligence is here. The question is, what kind of age will it be? That's for us to decide. And we'd better decide wisely, because the machines are learning fast, and time is running out to get this right. Welcome to the future. Let's make it a good one.